Okay, welcome to this video. This is going to review the notes we covered in class, Honors Physics. We will look at one final thing on projectile motion, then we'll move on to relative velocity. So watch in HD. First thing, let's say we have two marbles, and one will be dropped from rest, the other launched horizontally. Here's the one that's dropped from rest, and the one that's launched horizontally is here. So after a little bit of time, this one falls to here, and the other one is like here. After a little bit more time, this one is farther down, and this one is maybe here. And after even more time, they're here and here. And this is kind of a parabolic, well, it is definitely, not kind of, it is parabolic, the trajectory of the launched projectile, the launched marble, is parabolic. The cool thing is that they will hit the ground at the exact same moment. In fact, no matter how much time has passed, they will always be at the exact same height, the same level. Why is this true? The answer is simple. This marble has no initial velocity at all, so it has no initial y velocity. The y component of velocity is 0 because the whole velocity is 0 for this. And for the other, even though it has some initial velocity, it still doesn't have any initial y velocity. All of its initial velocity is in the x direction, causing it to have identical vertical motion as the marble dropped from rest. And if their vertical motion is identical, then their vertical height above the ground will also be identical at the same moment in time. So that is the last thing on projectile motion. We've done horizontally and vertically launched. Now on to the final topic, relative velocity. We're going to start by imagining something. Imagine you're in a hallway, a long hallway, and here you are, okay, with your locks of hair, and standing off in the distance at another end of the hallway is a person in a hat. And let's say the person in the hat is walking toward you and you are stationary. We put a little camera close behind you and we take photos periodically of what's happening. So here's our first photo, which I've shown. Oops. Now, after a little bit of time, here you are, right? We take a photo, you're still in the foreground, and after a little time the man has walked and gotten closer. So there's the man. And that's a little too tall. What happened to his neck? Why is it so long? That's better. If we wait a little bit more time, here you are, again in the foreground. The man is even closer, right in front of you now. There's the hat. So that's what it looks like from your perspective. And you seem stationary. In these photos, it looks like you're just standing in the same spot. You're not moving toward the man. The man moves toward you. So you're stationary. That seems like an obvious fact. It is obvious. But let's see what happens next. From the man's point of view, now let's imagine here's the man, and instead of putting the camera behind you, now we place the camera a fixed distance behind him. So at the beginning, here you are, you're far off. You're the one, beautiful locks of hair, there. And after a little bit of time has passed, we take a photo, again behind the man. The camera has moved with the man. And so So the man is still in the foreground because we're photographing from his perspective. And so now you're a little bit closer, like this. And if a little more time passes, here's the man again. The next photograph, he's still in the foreground. And you've gotten even closer with, wow, a giant head apparently. So even though the man was walking toward you in this case, if we take the man's perspective, here's the man's perspective, or the man's point of view, that's what's shown, the man's perspective. Even though he was the one walking, and you were the one who was stationary, it still seemed to him as though you walked and he stood still. So he seems to be stationary. If we take his perspective, it's sort of like he is stationary. This leads us to the first important definition, which pertains to relative velocity, and it's called frame of reference. A frame of reference. Here's the definition we'll be using in this unit. When you get into a college-level physics course, they will beef up the definition a bit, but it's going to be pretty close. A frame of reference is the perspective. It's a good way to think about it. The perspective of an observer or an object that is taken to be stationary. And stationary just means not moving, standing still, zero velocity. This may seem like a strange concept, frames of reference. I mean, after all, if I tell you a car is moving at 5 meters per second, I just say how fast it's going. I don't talk about a perspective. I don't talk about an observer. I'm not telling you something is stationary. I'm just saying the car's going at 5 meters per second. Well, here's the thing. We usually assume the ground to be stationary. Another seemingly obvious fact, right? We are assuming the ground to be stationary. In other words, we typically use the ground's frame of reference when discussing how fast things are going, when discussing velocity. And I know this seems obvious, but think about it for just a second here. Is the ground in fact stationary? Is it actually not moving? Or are we just taking it to be stationary, assuming it to be so? Well, we know that the Earth, here's the beautiful Earth, right? North America, kind of North America. You have to squint. Here's the ocean. We know that the Earth is is rotating about an axis. So it's spinning around, which means the ground is not stationary, it's moving. And here's the sun. Giant big sun. There's Mrs. Sun. Cool Mrs. Sun. So not only is the Earth rotating about its axis, it's also spinning around the sun. It's revolving at a huge, huge speed. Right? Going around the sun. So absolutely, the ground, from the sun's perspective, from the sun's frame, the ground isn't stationary. We just take it to be stationary when we talk about how fast the car is going. So there's a nice way that we can summarize this. Velocity of an object is relative to the frame that we're using, or as we say, the frame that we're in, which just means the frame that we're using. So, a great example, imagine there's a truck. Beep, beep. And a sunroof on the truck. Uh-oh, that seems dangerous. But, whoever made this truck put a sunroof in, and the driver sure is taking advantage. And there's the truck right there. Boom. In front is a car, which oddly has wheels larger than the truck's. That doesn't seem safe either. Poor designing in this case. And guess what? There's a sunroof on the car. So this truck is moving forward at 5 meters per second. The car is going at the same 5 meters per second. Relative to the ground, or with respect to the ground, or in the ground's frame, the velocity of the car with respect to the ground, or in the ground's frame, is 5 meters per second. But what's the velocity of the car with respect to the truck, or in the truck's frame? If they both move at 5 meters per second, then the distance between them never changes. So from the truck's frame, from the truck's perspective, with respect to the truck, the car doesn't seem to be moving at all. It's not going away, it's not getting closer. It's a fixed distance from the truck. And when something isn't moving away or moving closer, its velocity is 0. So what do we mean by the term relative? We mean that the velocity of an object changes based upon which frame we're in. That's what relative means. So let's put that down in our notes. The velocity of an object changes based on, or depends on, the frame we're in. And this truck car example demonstrates exactly that. This, right here, this, we capture with the word relative. So we're beginning to understand the concept. Now let's begin to derive some math. There are equations, there are problems attached to relative velocity. Before we get to the equations, let's consider some really simple, intuitive examples. Here I have the block there is a moving walkway, right? And the moving walkway is carrying the floor forward at 1 meter per second. There's a person, you see Justin Bieber, so you think, at the other side of the walkway, so you're running toward Justin Bieber. And what's your velocity? Let's do the velocity in a different color. Your velocity is 5 meters per second. And again, 1 meter per second for the walkway. So the question we have, how fast are you moving? What is the velocity of the person, you, with respect to the ground? Or, we can think of it, what's the velocity of you, the person, in the frame of the ground? In the frame of the ground. That's what we mean by with respect to. So, how do we find this answer? Well, you know what to do. This is really intuitive. You take the 5 meters per second, and you add the 1 meter per second to get 6 And that is correct.